Hello friends. So this is a session on Big Data, Hadoop and Spark. So this is the very first session, the introduction session, and you can even consider it as a demo session for the same. So I hope you have a slight idea on what is the boom of big data in today's industry. So we will talk more on that. So before going forward, let me introduce myself. My name is Sumit and I am the CEO and founder of Trendytech. Now, I completed my master's from NIT Trichy basically in the year 2013, and then I have worked for companies like Cisco and VMware, and I have worked on many big data projects. Now, I'm really passionate about this technology stack, and that's how I'm teaching, right? So, I have been teaching working professionals over the last 3 years in the same space, and I hold a very good passion to teach on the same. So I've trained around 2000 plus students over the past 3 years, and I have a consistent 5-star Google rating for the same. Now, you might have heard the term big data. So what is big data according to you? So if I ask this question to many people, everyone have their own answer. Some will say if the volume is very huge, it is big data. Some might say that if I'm not able to store the data on my laptop, it is huge for me, right? So we might get many definitions of the word big data. This is a very raw term. However, there is one formal definition which is given by IBM. IBM has given a very formal definition for the same. IBM says any data which can be characterized by three V's is considered to be as big data. Now we need to see what are these three V's as per IBM. And this is a very common definition. Many of you might be aware of it. So IBM says that if any data can be classified or characterized by these three V's stand for volume, variety, and velocity, then it will be called as big data. Now let us try to understand these three V's as per IBM. So with the name volume, it is very clear that the volume of data should be huge. That means it should be few terabytes, few petabytes like that. It's not small data. That means a single machine should be incapable of handling that. The volume is so huge. The name specifies it all. Now, if we talk about variety, variety says that data can be in different types. It can be structured, unstructured, semi-structured. It's not like traditional RDBMS systems or traditional SQL systems where we get the data in a structured format only. We have to handle unstructured plus semi-structured data also, right? So let's first talk about volume. You can see that the volume of data can be really huge, which our traditional systems cannot handle. You can see this, right? 2.5 quintillion, right? So it's very huge. Kind of with the traditional systems, we cannot even imagine to handle this much of load of data. So with variety, we have structured, semi-structured, and unstructured. So when we talk about structured data, the examples can be your RDBMS databases like Oracle, MySQL, or any other database. Semi-structured can be your CSVs, XMLs, and JSONs, right? You know that these have partial schema associated, not completely and not, I mean, it's not totally unstructured also, but a partial schema is associated with the CSVs, XMLs, and JSONs. That's why it is coming under category of semi-structured. Now, unstructured basically means your videos, your audios, even your log files. For example, if a web server is giving any logs, now, does that have any schema? No. So that is unstructured. So using our big data systems, we need to handle all these kinds of data. It's not just the structured data we need to handle. We have to handle all three kinds. Now comes velocity. So velocity basically refers to the speed at which new data is coming in. For example, let's consider that you are already handling 1 terabyte of data. But what about new data that is coming in with an increased pace? Can you discard that? No, not at all, because all the data is very important. You cannot discard any piece of it. Consider an example of Flipkart Big Billion Day. Don't you feel the velocity will be really high during those days compared to the normal days? Because someone like me, I mean, who never bothers to buy something, I am even tempted to see what is the sale going on and let me make a transaction during that day. So the velocity will be higher on some days and velocity might be low on some days, but the system should tackle that. So these are the three V's as per IBM: volume, variety, and velocity. If any data is characterized by these three V's, it is called as big data as per IBM. However, there are many variants of this formal definition floating on the internet. For example, you might see a definition with 4 V's, 5 V's, 7 V's, 11 V's. Now, we cannot go so theoretically, rather our approach should be practical, right? So 4 V's is still somewhat relevant. So let me just talk about it. What is the fourth V? The fourth V stands for veracity. Many of you might have heard about the three V's, but fourth V or the term veracity might be new to you. So let us talk about what is veracity. So veracity refers to the nature of the data, where we say data has poor quality. Let's say you have some data. There might be a lot of null values, a lot of missing values. Age might be negative. There can be n number of quality issues. And this is what is referred as veracity. So veracity refers to the nature of the data, where we say data is not clean. It is unclean. So poor quality data, unclean data. That means in big data systems, do not expect that you have high quality data. Your data might have poor quality and you might have to handle that. So we have talked about the four V's of big data as per IBM. Volume, which stands for really huge amount of data which traditional systems cannot handle. Variety, which means that we just do not have to handle structured data, rather we have to handle unstructured and semi-structured also. And third one was velocity, which refers to the speed at which new data is coming in. We need to tackle that. If the speed is high, we have to adopt to it. And fourth V is veracity, which refers to saying that the data has poor quality and we need to tackle it. Do not feel that data will be in the form which is desired. Data might not be in the desired form. Now these are the four V's as per IBM, and this is one of the formal definitions, so I thought of letting you know. Now everyone is tempted to learn big data technology. I understand we learn this in order to upgrade our career, to get new jobs, better hikes and all, fine. But what is the business goal that you are trying to solve using this? Try to think that. So what there should be a problem statement you are solving by learning a particular technology. What is that problem statement? So just think of one line problem statement that you are trying to solve by learning this big data technology. So if you ask me what is the whole purpose of learning big data, it is just one purpose, that you will be able to process or you will be able to crunch huge amount of data which you cannot do using the traditional systems. There is nothing more than this. You want to process huge amount of data which your traditional systems were not capable of doing. As simple as that, right? So the requirement is very clear that why you are using or learning all these big data technologies is you want to process huge amount of data which traditional systems cannot do. Now I understood that traditional systems cannot process huge amount of data. But don't you feel before this there is a prerequisite? The prerequisite before processing is storage. That means if my traditional systems cannot process, they cannot store also. I mean, if I have, let's say, a laptop with 1 TB hard disk, and I am getting a data of, let's say, 1000 terabytes. Can I store this 1000 terabyte data on one laptop? No, because my laptop is capable to handle 1 terabyte only, let's say. Then how can I store this 1000 terabytes on a single machine? That means my traditional systems cannot even store the data because data is so huge that it cannot be stored on a single machine. So before thinking about processing, we need to worry about storage because our traditional systems cannot even store huge amount of data. We need a different system, right? So to process huge amount of data, first need to store it. So before worrying about processing, let's worry about storage. Because first you need to store and then you think about processing, because it's a step-by-step procedure. You cannot first process and think of storing, right? The data should be kept somewhere. So first your worry should be you want to store it in a very nice manner somewhere, and then you want to process it once the data is stored properly. So first storage and then processing. So are our traditional systems capable to store such massive amount of data? No, not at all, right? So traditional systems are not fit to store huge amounts of data, as mentioned. So the first thing, or let's say if someone asks you that, can you design a good big data system? Then the very first thing you need to worry about is storage. That means if someone is referring to big data, how will I store that big data? Because my traditional systems cannot help me out. So the first thing you need to worry about is storage. Store massive amounts of data in a proper way, right? Now, once storage is tackled, you need to worry about processing. Because you have said, okay, my storage is done, let me worry about processing, right? So now you need to worry about processing or a way that you are able to handle this data, right? Now there is a third requirement also, which you might not feel it's intuitive, but it is very, very important. The system should be scalable. That means, let's say today your manager asks you that, can you design a system which can handle 500 terabytes of data? Now you have designed a very fancy, beautiful system which can handle 500 terabytes of data. Fine. Tomorrow your manager comes back to you and say that our requirement has increased 10 times. Our requirement has increased 10 times, and instead of 500 terabytes, the requirement is to handle 5000 terabytes. 10 times. Now you cannot wave your hands and say, boss, you gave me a wrong requirement. No, you cannot do that. You cannot afford doing that, because this is IT where the requirements keep on growing. You have to tackle that. That means with the changes or with the growing needs, your system should adopt. If the requirement increase, you need to make sure you are able to accommodate that somehow. If you are able to accommodate the growing demands, then it is called as a scalable system. If you are not able to do that, then it is not scalable. So you need to make sure a good big data system is always scalable so that it can adopt based on the growing needs. Because if it is not scalable, then this system might work today, but not tomorrow. So I hope I am clear with this. So basically, there are three things you need to think of when designing a good big data system. Storage, because your traditional systems cannot store the data in a proper way. Processing, because your traditional systems cannot process it. And third is scalability. That means if the requirement grows, you need to tackle it in a very efficient way. So store, process, and scale. These are the three things required to design a good big data system. You can just have a look at this slide. It should give you a clear picture. Now, why we are not able to store and process? Because data is so big. We are not able to store it, in a single machine somehow. Okay. Now, let us come to this thing. Here, storage and processing seems to be very easy and intuitive to understand. Scalability might be a little confusing. That is why I have some more content around it. Now, when we talk about scalability, it's a good point to talk that a system can be designed ideally in two styles, or there are two ways to design a system: monolithic system and a distributed system. You might have heard or read it during your academics and all. Now let us try to understand what is monolithic and what is distributed. So with the name mono, you might know mono means one, right? This clearly indicates this is one system, but ideally a very powerful big system. So mono means one. So ideally monolithic system is a one powerful big system, which is holding a lot of resources. I will tell what is resources. But for now, understand that monolithic means one big powerful system, just like shown in this case. On the other hand, distributed means many systems, but ideally smaller systems. And each system ideally or technically is called as a node. For example, this might be node 1, this will be node 2, 3, 4, 5, 6. This is a 6-node cluster. Together it is called as a cluster. So distributed systems is nothing but many smaller systems coming together to solve a purpose. And each system or each small system is called as a node. And together it is called as a cluster. So in this case, what you see on the screen is a 6-node cluster. Right? So you understood what is monolithic. Monolithic means one big powerful system holding a lot of power. Distributed means many smaller systems coming together to solve a purpose. Together it is called as a cluster. Now, which system is better, monolithic or distributed? We need to think of it. Now, as you know, monolithic means a single powerful server holding a lot of resources. But let's say tomorrow, if you want to scale it or add more resources to it, is it easy? No, not at all. Consider your laptop. If you have a laptop with, let's say, 16 GB RAM, tomorrow you want to upgrade it to 32 GB, might be it's possible. Okay, it will happen once. Again, if you want to upgrade it to 64 GB, okay, it might happen. But after a certain point, you might not even be able to scale that. Or even if you're able to scale, it might not perform accordingly. There are limitations with a single system and when you try to keep on dumping resources. So when I say resources, I mean three things. This is a very important term you need to remember. What do I mean by resources? Because I'll be using this term resources many times in this course. So when I say resources, I would ideally mean three things. Your RAM, for example, let's consider it with your laptop. You might have a 8 GB RAM in your laptop. Hard disk, you might have a 1 TB hard disk. And CPU, you might have a quad core processor, 2.31 gigahertz and all, right? So these are the three resources we talk about: RAM, hard disk, and CPU. Now, technical words used for it is RAM is called as memory, hard disk is called as storage, and CPU is called as compute. So memory, storage, and compute forms the resources for you. Now you can relate it to your laptop so that things are easy to understand, right? For example, if you ask me, my laptop has 16 GB RAM, that means memory is 16 GB, hard disk I have is 500 GB, so storage is 500 GB, and CPU is quad core. Again, compute is quad core. So these are the resources I'll be referring to in the course throughout. Now, the problem with monolithic is that it is not scalable. The reason why I'm saying it is not scalable is a scalable system is something where when you double the resources, the performance should be double, right? Because if I double the resources, that means I'm spending twice on the system. I'm investing double. That means I should get double the performance easily. But with monolithic system, it is seen that after a certain point, if you keep on adding or doubling the resources, the performance is not doubling up. Let's say you might double the resources, the performance might be 1.5 times. That means even though you are adding more and more resources, but the performance is not growing according to that. That means, it is not utilizing your resources in an efficient manner, or it is wasting some of your resources. That is why we say that monolithic cannot scale after a certain point. And this is the reason why you do not see a system with, few TBs of RAM. At least I have never seen. I have only seen systems with 64 GB RAM, 128 GB RAM at the max. Have you seen a system with 4 TB RAM? No. The reason being, even if you see 4 TB RAM in a laptop or somewhere, it might not justify for the output or performance. Right? So monolithic is not scalable. That means when you double the resources, the performance does not double. On the other hand, let's say you have a distributed system with 6 nodes, right? With 6 machines. Now, if someone asks you, can you double the performance? It is very, very easy. You just need to bring 6 more machines so that total number of machine becomes 12, right? Because this is a scalable system. So you can see this. If someone asks to double or the performance, what we need to do is add 6 more nodes to this cluster so that it has 12 nodes, and then the performance will be double or speed will be double. Now, even if let's say you have a 500 node cluster and someone asks you that can you double the performance, you make it 1000 nodes. That means it can scale linearly. There is no dip in performance. And that is why all the big data systems or all the good big data systems are based on a distributed architecture. The reason is scalability, because distributed architecture gives you true scalability. So you can see this monolithic architecture, and when we keep on dumping resources to a single machine, we call it as vertical scaling, because vertically we are trying to add more and more resources. And this is not true scaling, by the way, because after a certain point there is a dip in performance. However, in case of a distributed architecture, if we add more machines, it is called as horizontal scaling, because we keep on adding more and more machines. We are not adding resources to the existing machines, rather we keep on adding new machines. And this is called as horizontal scaling, which is true scaling. Even if we have 1000 machines and we want to double, we can easily do this. Now, I hope you are clear with monolithic versus distributed. So basically the point here is that all the good big data systems should be based on a distributed architecture for getting true scalability. Because in IT, the requirement keeps on changing and you cannot get stuck with the old requirements. So throughout this course, we will always talk on this distributed architecture. We will never talk about monolithic architecture. So you can see this. We will never talk about monolithic, always distributed to get scalability. That is why all good big data systems are based on distributed architecture. Now, this has given you a good background that why, or first of all, we covered what is big data as per IBM, the 3 V's and 4 V's. And then we talked about what is the problem statement we are trying to solve. The problem statement we were trying to solve is we want to process huge amount of data. Now, before this comes the challenge that how are we going to store it? So we need to first think of storage, then we need to think of processing, and then we need to think of scalability. And that's what we have talked about. And for scalability, it is said that we should not go with monolithic systems. We should only go with distributed systems because those are scalable, truly scalable. So let's take a pause here and then let's continue with Hadoop. So I hope you have understood that what exactly is a distributed architecture. Now let's talk about what is Hadoop. Can you think of a one-liner definition of what is Hadoop? If you ask me, I will say Hadoop is a framework to solve big data problems. As simple as that. Hadoop is a framework to solve big data problems. Now, why do I say Hadoop is a framework? Because Hadoop is not just one thing that you learn and done. No, it is a bunch of tools and technologies which come together to solve a purpose. That is why I say Hadoop is a framework, not just one thing. There are a bunch of things inside Hadoop which we will be looking at shortly. You do not have to worry about it right now. Right? Now, all the things in this framework are there to solve problems related to big data, nothing more than that. So that is why a single line definition, Hadoop is a framework to solve big data problems, because we are going to deal with big data using this framework related technologies. Now, before talking about Hadoop in a lot more depth, let's see how Hadoop evolved. Now, basically, Google in the early 2000s realized that whatever processing they have to do to make their existing web search work won't scale based on a monolithic architecture, because Google till that time was based on a monolithic architecture, and they felt that with the growing needs, this monolithic architecture won't help, and it won't help them to scale. So they felt the need of distributed computing then. And in the year 2003, Google released a paper, or basically a white paper. White paper is nothing but a theoretical concept given to the outside world, saying this is how we can do the things, but the implementation is not released. So in 2003, Google gave a white paper or a theoretical concept to the outside world, saying if you have huge amount of data, how you can store it in a proper way, right? For example, let's say if you have 10 terabyte of data and you have 1 terabyte of hard disk in a laptop, can you store this 10 terabyte data on one machine? No. So Google gave an idea that how you can divide this 10 terabyte data into multiple small parts and give it to different machines. So this was the idea given by Google, right? So Google gave a paper related to storage, that how to store huge amount of data on a cluster of machines. That means you might have a 10 node cluster. You remember we said that we will be dealing with distributed architecture. That means we will be having more than one node. Let's say there are 10 machines. Now what Google said, that is there a way that we can divide this big file into 10 small parts or more small parts and give each part to a separate machine. So this is what they talk about in this paper. Now consider a very simple example. You have 10 machines with 1 TB hard disk, and consider you have a file with 10 or size of file is 10 terabytes. Now can you store this 10 terabyte file on one machine? No, not at all. That means what Google said, that is there a way that we can divide this 10 terabyte file into 10 parts, each of 1 terabyte, and give it to a separate machine in the cluster. So this is what they talked about in this GFS paper. And this GFS stands for Google File System. So the name of this paper on distributed storage is called as GFS, which stands for Google File System, where they talk about that if you cannot store the data on one machine, how you can divide the data and store it on multiple machines. Now, you remember when we talked about what are the requirements to design a good big data system, there were three things we need to deal with. The first one is storage, which they have covered here. Second one is processing, and third one is scalability. Now, scalability will be taken care because whatever they are giving is based on a distributed architecture. So scalability is taken care. Storage they have given already. Now what is remaining is processing, and that's what they have given in the year 2004. In 2004, they said, okay, we have already stored the data. We have already stored the data on a cluster of machines in a scalable manner. Now let us worry about processing it. And this time they gave a paper on distributed processing. You can think it that whatever C program, Java program, Python program you used to write, used to take the data from one machine and solve the problem. But now things are no longer the same. The data is not sitting on one machine anymore. The data is sitting on multiple machines. And that is what they have given an idea, that when data is stored on many machines, how to process the data. Because your traditional programming models do not work now. Your traditional programming models only work when data is stored on a single machine. Data is stored on a multiple machines now, so your traditional programming models do not work, and a new programming model was required, and that is what they have given in the year 2004. And this paper on distributed processing is called as MapReduce. If someone is very curious, you can see HDFS and MapReduce paper on Google. The official papers will be available. GFS paper and MapReduce paper on Google. GFS is for distributed storage and MapReduce is for distributed process. These are the two papers given by Google. Now these are just the papers. Now papers are good to some extent, but someone should implement, and that's where Yahoo came to help. So what Yahoo did is that in the year 2006, Yahoo took these two papers given by Google. Right? Google gave the papers in 2003 and 2004. The papers were GFS. GFS was for distributed storage and MapReduce for distributed processing. But those were just the theoretical concepts. Yahoo took these papers and they gave implementations or built softwares on top of it. Right? So the implementation of GFS was named as HDFS. That means Yahoo took the GFS, Google File System paper, they implemented it, and the name they gave to this is HDFS, which stands for Hadoop Distributed File System. Many of you might have heard this term. Also, they took the paper MapReduce, they implemented it, but in this case, they have not changed the name. The name is still kept as MapReduce even after the implementation. That means from GFS, we got HDFS as the implementation, and from MapReduce, we got MapReduce as the implementation. So basically, we have two things now. HDFS. What is HDFS for? Distributed storage, because data is not stored on one machine. Data is stored across many nodes across the cluster. And we have MapReduce. MapReduce is for distributed processing because data is kept on many machines. Now there is a requirement for a processing model which can take the data from many machines and process it. And MapReduce do that. None of your traditional models do that. So HDFS is for distributed storage and MapReduce is for distributed processing. Right? And these two form the core components of Hadoop in the very first version of Hadoop. So if someone asks you in the very first version of Hadoop, Hadoop 1.0, what are the two core components? So the two core components of Hadoop 1 are HDFS and MapReduce. HDFS is for distributed storage and MapReduce is for distributed processing. So I hope you should be very, very clear with this now. Right, so you understood that we get this HDFS and MapReduce, and these two form the core components. Now, in the year 2009, Hadoop came under the Apache Software Foundation and became open source. That means from 2009, it became open source and anyone can see the source code and anyone can contribute to it. There is a difference between free and open source. Free means you can use it freely. Open source means you can even contribute to it. The source code is available publicly. For example, tomorrow, if you see some bug in Hadoop, you can report it, you can solve the problem, and you can even code for it. Right? Now, in the year 2013, Apache released Hadoop 2.0, the second version of Hadoop, which has major performance enhancements. We will talk on this later in some time. So this is how the Hadoop evolution is. In 2003, Google gave a paper on distributed storage. In 2004, Google gave a paper on distributed processing. And in 2006, Yahoo implemented these papers. And then 2009, it became open source. And 2013, we got Hadoop 2.0 with major performance enhancements in Hadoop 2.0. Now, this is what the difference is between Hadoop 1 and Hadoop 2. Now, let me tell you what was the main challenge with Hadoop 1. The major problem with Hadoop 1 was that they felt, or the architects felt, that this MapReduce is a very bulky component, or MapReduce is such a big component that it has to do a lot of activities, and it was getting stuck there or getting bottlenecked there. If someone has to do a lot of work, right, it gets bottlenecked unnecessarily. So what they felt is that, is there a way we can break this Hadoop, or we can break this MapReduce so that we can take some portions of its work and give it to a new component. So consider, let's say if MapReduce was doing 100 things earlier, what they felt is that, is there a way that we can take some 40 activities from this so that MapReduce can work only on 60 easily, and the remaining 40 we can give it to someone else. So that is what they did for. So what they did is they broke this MapReduce into two parts. One is still called as MapReduce with a limited set of functionality, and another one is called as Yarn. So that means Yarn took some of the capabilities of MapReduce and came as a new component. But having said that, Yarn possessed some new capabilities also, which were never there in MapReduce. That means Yarn possessed some capabilities of MapReduce plus some new capabilities also, which were never there. So this is one of the change in Hadoop too, that Yarn was introduced and MapReduce functionality was split into two parts. Now we will see what is Yarn in some time from now. And also do not feel that this is only one of the change between 1 and 2. As of now, we have seen one change. Later throughout the course, we will see multiple changes which are, or multiple differences which are there in Hadoop 1 and 2. This is just one of the main architectural change that Yarn was introduced. So what is Yarn? We need to understand that. So before that, let me ask you, what is Windows on your system? Windows is nothing but an operating system, you know that, right? Windows is operating system. What is the role of Windows, or what is the role of operating system? Operating system is mainly used to manage the resources efficiently. For example, if I'm using Windows, then it will help me to manage the resources on the system in a very graceful way. Think Yarn like an operating system only. But Yarn is not just running on top of one system like Windows. Yarn is running on top of multiple systems or across the cluster. For example, let's say you have a cluster of 100 nodes. So think Yarn is an operating system sitting on top of those 100 systems or 100 nodes and managing the resources underneath. That means it does not manage the resources of just one single machine. It manages the resources of all 100 machines as a pool of resources. That means if someone needs resources, they will contact Yarn and say, can you give me resources, please? Yarn is the sole owner of the resources and will manage the resources in an efficient manner. The full form of Yarn is yet another resource negotiator. That means if someone wants resources, they will negotiate the resources from Yarn. And Yarn is mainly responsible for resource management. That means Yarn is nothing but a resource manager or like an operating system in a distributed environment. So this is how it looks like, or the three core components of Hadoop looks like in the second version of Hadoop. Because in first version only HDFS and MapReduce were there. But in the second version of Hadoop or Hadoop 2.0, we have three core components. HDFS for storage, or I should rather say distributed storage. MapReduce for distributed processing, and Yarn for resource management, just like an operating system. This is the diagram I'm showing you for Hadoop 2.0. So if someone asks you, can you tell me what are the three core components of Hadoop in the second version of Hadoop? The three core components are HDFS, MapReduce, and Yarn. HDFS is for distributed storage, MapReduce for distributed processing, and Yarn is a resource manager. Now, if someone has some idea about Hadoop or big data, you might have heard of variety of things like Hive, HBase, Pig, Scoop, Flume, Oozie, Zookeeper, Spark. A lot of things are there. Let us understand what are these things and how does this things fit in with Hadoop. So basically, we have the Hadoop core with three things: HDFS, MapReduce, and Yarn. And there are a bunch of ecosystem technologies that surround it. And this is how it looks like. Some of the crucial or important ecosystem technologies which you should know are Hive, HBase, Scoop, Uzi, Pig. Even though I have kept Pig, but Pig is not that important these days. Spark. Spark is very, very important, right? We will talk more on that. But think that these are the ecosystem technologies surrounding the Hadoop core. At the core of it, or at the heart of it, lies the Hadoop core. And there are a bunch of ecosystem technologies which surround. And this together is called as the Hadoop ecosystem, as mentioned here. So if you encounter this term Hadoop ecosystem, this is what it looks like. Now let us try to touch base on this ecosystem technologies at a very high level. Now let me tell you one thing, or let me ask you one thing. What is the processing unit used in the Hadoop core? Now everyone knows it is MapReduce. Now what is the kind of code we have to write for MapReduce? In which language we need to write? Or in which programming language we need to write? So the code written for MapReduce is mostly in Java language. And Java is not something which everyone is familiar with. Most of you might not be aware of Java. If you do not know Java, does that mean you should not be able to work on Hadoop? No, absolutely not. It does not mean that. Hadoop should be open to other people also who do not know Java. And that is where Hive comes for the rescue. Hive says that, boss, okay, no worries if you do not know Java. If you do not know Java, at least you might be aware of SQL. Is there a way that you can write SQL and I can convert it to the hard written MapReduce code internally? That means Hive is nothing but a wrapper on top of MapReduce. You write the code in SQL style, which you are very familiar with, and Hive internally will convert it to Java MapReduce code and trigger it on the cluster. That means all the complexity of traditional MapReduce is hidden from you. You do not see it as MapReduce, but internally it will happen in the MapReduce. So what Hive says that you write the code in SQL style and I will convert it to MapReduce code and I will execute the job on cluster so that all the complexities will be hidden from you. I will do the hard part and you do the simpler part. So Hive is very, very important and is something very crucial in this entire course. A lot of companies ask many questions on Hive and they ask a lot of things like what is partitioning in Hive, what is bucketing, what is map side join, what is bucket map join, what is SMB, what is vectorization, what is file formats, how to create your Hive own UDF. A lot of things will come in Hive which are very, very important. So Hive is something which is very, very important, but for now what you should know is it is more like SQL and you will be able to query your data in a very graceful way. Now you understood Hive. And one more point I want to convey is Hive was developed by Facebook. If you are curious to know, Hive is developed by Facebook, right? So in our Hive lecture, we will cover Hive in a lot of detail. I mean, there won't be anything which is left untouched. That's how the depth will be. Now, having understood about Hive, so remember one thing, I said underneath Hive jobs are MapReduce. If you feel that you want to do it in Java code, you can feel free. But think that who will write 200 complex lines of Java code when you can do it with one single line of SQL? Even if you are a hardcore Java developer, you will say, okay, why not I write simple SQL kind of query and do it? And remember, till now I was saying SQL. It is actually not SQL, it is HQL, which stands for Hive Query Language. And it is very similar to SQL. If you know SQL, think that you know HQL. That's how similar it is. But technically it is called as HQL, Hive Query Language. Okay, so we have covered Hive to some extent. Let's talk about Scoop now. So basically, what is Scoop? Now, I always try to give it with this example that let's say when you go to ice cream shop, you say, give me one scoop of ice cream. They take the, scoop from the container and then they put it on the cone. That means they transfer this ice cream, right? So think scoop is to transfer. Remember this, scoop is to transfer. And what it transfers data from your traditional databases to your Hadoop environment. That means, let's say today you have some data in your Oracle database, or you have some data in your MySQL database, and you want to get it to your HDFS. How will you get it? Using scoop commands. Let me go back to this scoop. So a command line interface application for transferring data between relational databases and Hadoop. That means if your data is in MySQL or if your data is in Oracle or any other database and you want to bring it to Hadoop, or if you want to bring it to HDFS, because when we say Hadoop, where is the data kept? It is in HDFS. So a scoop is to transfer data from traditional databases to HDFS. And even you can do it vice versa. That means if your data is in HDFS and you want to send it to databases, you can do that also. So it is a command line interface to do these things. And it's very easy, but very, very important again from industry perspective. So scoop is for data ingestion or data migration. You can think it this way, right? So you have understood Hive. What is Hive? Hive is nothing but to query your data on HDFS, right? Rather than writing complex MapReduce, you want to do it using Hive, right? Because you are more comfortable with SQL. Scoop is for data ingestion from databases to HDFS. Now, what is pig? You need to understand this. Before telling this, let me tell you, pig is not something which is important now. In today's world, not most of the companies use scoop. So scoop is, So in today's world, not most of the companies use pig. Pig is not something which is important. So basically, pig earlier was there to solve two major purposes. The two major purpose that pig used to solve is, let me just make a note here. So pig used to solve two purposes. One is to clean the data, and second purpose for pig was to convert structured data to convert unstructured data into structured. Even though pig is not important, I want to give you an idea about what pig was doing earlier. So you remember in the very first slide we said the fourth V was veracity. That means data might be unclean. Then you require a ETL kind of utility or tool to clean the data. So pig tried to clean the data, or is like a ETL using some scripting language. And the scripting language is nothing but pig Latin. This is the name of scripting language. So we used to write scripts in this pig Latin language, and we used to clean the data. And this is nothing but a ETL utility using scripting. Also, we used to convert unstructured data to structured form. For example, let's say you are getting some web server logs. Now, web server logs, do not have any structure. But technically, if you open the file, the first column is an IP address. After that, there is a space, then there is some what kind of request it is. Like it can be something like IP, then after that kind of request, right? And then after that date, and then there is some tab, after that something. Technically, you know the structure when you open the file. Then if you can write the same thing in the script, then you can create a table from this kind of data, right? That means you can convert this kind of unstructured data into a table. So converting unstructured data into structured form. So you can have a look. A scripting language for data manipulation also transforms unstructured data into structured form. Now let me ask you a question. Is Pig internally a MapReduce? We said Hive internally is a MapReduce. Is Pig also a MapReduce? Yes, definitely. Pig is also a MapReduce underneath. It is an abstraction of MapReduce. That means if you want to do the same things using MapReduce Java code, you can do that also. But who will write 2000 lines of Java code when you can do it with 5 or 6 lines of big script? Think it this way. So this makes life easy for a developer. So Hive, Pig, Scoop, all these things makes life easy for a developer because you are able to do it in a quicker time using much more lesser code and all. So by the way, let me tell you, the demand of Pig is almost zero in today's industry. You might have a question in mind. Then if Pig is not used today, then how are we doing these two things? How are we doing these two things which we were doing using Pig? The answer is these two things are now done mostly using Apache Spark. We'll talk about it later, but remember that Apache Spark will do your data cleaning, and Apache Spark will also help you to convert unstructured data into structured. Pig is kind of not used. Now, if I ask you what is Spark, you might frame a definition saying Spark is a replacement of Pig. But this will be a wrong definition because Spark is not just these two things. Spark can do hundreds of other things also. So you cannot yet form a definition of Spark. But I can definitely say whatever we were doing using Pig, Spark can easily do that. Plus, Spark can do a lot of other things also, which we will talk about later. So we talked about Hive, we talked about Pig. Hive is nothing but querying of data in SQL-like format when you do not want to write MapReduce. Pig is nothing to clean the data and convert unstructured data to structured form, mostly not used these days, and Spark can do these things. Now, Scoop, as I said, is for data ingestion. If you have your data in traditional databases and you want to bring this data to HDFS, you can write Scoop commands to do that. Now let me ask you again a question. Is Scoop also MapReduce? We understood Hive was MapReduce internally, Pig was MapReduce internally. Is Scoop also MapReduce? So the answer is yes. Scoop is also a MapReduce job. Scoop is also a MapReduce job. And this is a special MapReduce job. As of now, whatever I'm thinking, I'm telling you, but if you, I mean, just try to make a note of it for now. So Scoop is a special MapReduce job where only mappers work, right? It is a special MapReduce job where only mappers work. As of now, since I have not explained you what is map and what is reduce, you might not understand, but it is worth to take down this line that only mappers will come into play. There is no role of a reducer. And you will understand this later when we understand what is map and what is reduce. So Hive is a MapReduce, Pig is a MapReduce, even Scoop is a MapReduce, but it is special in the sense only map will work, reduce won't. So Scoop is for data ingestion, getting the data from databases to your Hadoop environment. Now, what is HBase? I won't talk much about it because the context is not set. However, I will just tell for now is HBase is a column-oriented NoSQL database. You might have heard of MongoDB. Let me relate it with MongoDB. MongoDB is a NoSQL database, right? Similarly, HBase is also a NoSQL database, which runs on top of Hadoop. I won't tell more for now because as of now, we have not set the context, right? So I won't talk more. We will discuss on this later in a much more depth. But for now, what you should know is HBase is a NoSQL database which runs on top of Hadoop. Now, what is Oozie? Now consider that you have created a job, MapReduce job, and you want that job to run 8 p.m. every day. Now, will you go to your laptop and trigger that job 8 p.m. every day? No. Rather, what you will do is you will try to schedule that job, right? So you will want to automate things, right? And that's where you use schedulers like Oozie. So Oozie is nothing but a workflow scheduler, which is which will help you to manage and schedule your jobs. As simple as that. There is nothing so crazy about it, right? It is something like a scheduler which will help you to schedule things on time. Now we understood what is Hive, what is Peak, what is HBase, what is Scoop, all those things. Now we need to understand what is Apache Spark. And remember, this is more important or most important thing in the entire big data ecosystem. This is one of the most or the hottest technology of today. So we have talked really great about Spark. So now this is the time when we should learn or understand what is Apache Spark. So in one line, if I have to give the definition of Apache Spark, I will say Spark is a general purpose in-memory compute engine. My one-liner definition is Spark is general purpose in-memory compute engine. I'm using three keywords here. General purpose in-memory compute engine. Let's dig down into each of this. Apache Spark is a general purpose in-memory compute engine. This is what I said. Now tell me, what are the three things Hadoop gives you? Hadoop gives you HDFS, MapReduce, and YARN. These are the three core components of Hadoop. Now HDFS is the storage unit, we know. MapReduce is the computation unit, and YARN is the resource manager. We know this very well, we have covered. So what is the compute engine here? MapReduce. Now what we say, Spark is nothing but a general purpose in-memory compute engine, right? That means Spark is nothing but, we can say, a replacement of or alternative of MapReduce. You can think or you can compare MapReduce with Spark, because in Hadoop, what is the computation unit? MapReduce. Spark is also just a computation unit, nothing more than that. So if someone compares Spark with Hadoop, then those people are wrong, because Hadoop gives you three things. How can you compare storage, processing, and resource management with just computation? Because Spark only gives you one thing, that is computation, right? You cannot compare three components with just one component. Rather, what you can compare is computation with computation. So if someone compare Hadoop with Spark, that is wrong. We cannot do that. But if someone compare MapReduce with Spark, that's perfectly fine, because we can say Spark is a replacement of MapReduce, right? So you can see this. So what in industry people do majorly is they remove this MapReduce and bring in Spark. So the things become HDFS for storage, Spark for processing, and YARN for resource management, right? So they normally remove MapReduce because of some of the drawbacks of MapReduce, and we will talk about those drawbacks later. But remember, Spark is much more better than MapReduce, and this is the current industry architecture: HDFS, Spark, and YARN. So instead of MapReduce, we bring in Spark here for computation. So now what Spark says? Spark says I am just a plug and play component. That means you just need to add two things, because I am just a compute engine. You need to give me two more things to work. And those two things are storage and resource manager. So you can have either HDFS as the storage, or you can have, so I might have a slide for that. Yeah. So Spark says, I am just a plug and play component and I need two more things to work with, because alone computation cannot do anything. So Spark needs two things to work with. One is storage, which can be either your local storage, your HDFS, or Amazon S3. And it needs one resource manager to manage the resources. It can be YARN, or it can be Mesosphere, it can be Kubernetes. You do not have to worry too much on this. Mostly your Hadoop admins will decide it. Your code and all won't change at all. So Spark says, I am just a compute unit. I need two more things. One is storage, one is resource manager feel free to give me any of those. I will work fine. I am not tightly coupled with any storage and any resource manager. You can give these things based on your choice. So this is how it will look like. So you see, compute unit will be Spark. Your storage can be either local storage, HDFS, Amazon S3, and your resource manager can be Yarn, Mesosphere, or Kubernetes. Now, if we use storage unit as HDFS and if we use resource manager as Yarn, we say it as Spark on top of Hadoop because Yarn and HDFS are part of Hadoop. Think it this way. So if you ever hear this term Spark on top of Hadoop, what does that mean? That means we are using resource manager as Yarn and we are using storage as HDFS. And now you might have got a clarity that Spark can run without Hadoop also. That means if we are using Amazon S3 as storage and if we are using, let's say, Kubernetes as resource manager, then don't you feel that Spark is totally separate now? Hadoop has nothing to do with it now. So Spark is not always dependent on Hadoop. However, you can combine these two things when you use Yarn and HDFS along with Spark. So this is how the things looks like. So I hope you are good with this. So what we have discussed is the first point. I said Spark is not a replacement of Hadoop because Hadoop gives you three things and Spark gives you just one thing, that is compute engine. If someone compares MapReduce with Spark, that is perfectly fine because MapReduce is the computation side from Hadoop and Spark is again a compute engine. We can compare compute with compute. Now this is how things looks like. I have explained this, and this is the current industry trend most of the times, and this is called as Spark on top of Hadoop because these two things we are taking from Hadoop, the storage and resource manager. Now you might have a question, in which language Spark code is written? Now basically Spark code can be written in multiple languages. Spark code can be written in Scala. Spark code can be written in Java, Python, or R. There are four languages which are supported: Java, Scala, Python, and R. R is mostly for data scientists. It is not in our portfolio at all. However, having said that, the most famous choice for data engineers is Scala. And that's why when you see most of the job openings, they will ask Spark with Scala. This is the buzzword in itself. There is no other language which goes with Spark so well. So Scala with Spark is the top choice. Reason being, Spark itself is written in Scala, and moreover, it gives you the best performance. And the next choice is Python. The second choice is Python, and that is what is called as PySpark, right? In our course, we will be looking at PySpark also to some extent, so that in interviews, if they ask questions, you are able to answer them also. However, our top choice will be Spark with Scala because that is the most demanding thing. Now, I hope you have understood all these things. For the time being, we have covered at a very high level. In our course, we will be digging down into each topic in a lot of depth so that we are in a position to crack top companies. Now, let me introduce little about my course. So basically, I have been teaching or I have been training students for the last 3 years now, and I have a consistent 5-star Google rating. You can check that on Google, right? I have around 300 plus reviews, and you see I have a 5-star consistent rating. Now, this course is a 15 weeks extended course online. This is a 15 weeks extended course. That means the duration is really high when you compare it with other courses because I want to cover things in a lot of depth. I want to cover things in a way that after doing this course, you should not feel that this is left. After this course, you should feel that you are job ready and you should be in a position to crack top companies with ease. You should have multiple offers. That's how the intention is to design this course, right? And this is mostly suitable for working professionals. However, freshers can also do it, but for freshers the effort that they have to put will be little bit more. It is specially designed for working professionals, mostly for people who are working on Java or SQL, database, data warehouse, ETL, all these people. I mean, it is specially designed for you. However, having said that, I have even trained people who are completely from non-IT background and who are working with top packages now in top companies. So my style of teaching is something which you will appreciate throughout the course. And this will be 150 plus hours of quality learning, and the course has been designed with a lot of thought process going behind, so that we pick only the trending things. It's not something we teach blindly. It won't help. Rather, it comes with the intention that this thing should be trending and asked in interviews, or you should be using them in projects. So this is how it is. Now the plan will be that each week I will be giving a set of recordings. I never prefer live sessions because live sessions seems to be a word which is tempting sometimes. But normally what happens, people join live sessions in institutes and then they do not get time to attend those sessions live. And they have to finally rely on recordings, and recordings are not that great that they can make the most out of. So I have talked to a lot of working professionals on, I mean, their behavior of learning and all. And I thought, why not give them some quality learnings or quality videos at the start of the week, and they have to complete those videos by the end of the week. And if they have any doubt in the meantime, or if they have any ad hoc doubts, I'll be assigning dedicated student mentors whom they can reach out to. And those student mentors will guide you at your earliest convenience. Right? For example, you are stuck in something and you want immediate help. You can reach out to your student mentors, and your student mentors will help you whenever fastest possible. Might be they can help you in 2 hours from now, because my student mentors will also be working professionals, right? So that's how it will be. And also at the end of the week, there will be a dedicated doubt clearing session, which will be live. You can ask all your doubts in that doubt clearing session so that all your doubts are rectified. Even though it is recording based, but this ownership or this guarantee I take that no one will get stuck. Everyone will be able to execute every code. That is my guarantee. I won't leave you behind. I mean, I will go along with you. I will make sure if you have any doubt or if you have any issues, I will help you personally. That's how it is. And this will make sure that the learning is quality learning, and you can see the videos at your pace. Per week, the effort required will be 10 to 12 hours at least. So make sure if you are taking this course, 10 to 12 hours per week will be required. I mean, you cannot just think that I mean 2-3 hours per week and done. No, this is something I have designed that will require effort, but this effort will be really fruitful. A 15 weeks duration with 10 to 12 hours per week can make you so strong that you will be in a position to crack top companies with ease. Now, I will include both Hadoop, Scala, Spark, Big Data on AWS Cloud. All these things are covered in this. Now, normally what others offer is separate modules. My intention is not that. I want to give you a full-fledged course which covers all the things in depth, right? A single course which should meet the requirement for you to crack top companies. That's what my intention is. Even you see big data on AWS Cloud, which is something very trending. I have included it, and it will be in depth. Your Redshift, Athena, Glue, all these things will be covered. S3, EMR, right? All these things will be covered in a lot of depth. Now it will be a total hands-on learning. I do not believe on theory. It is full hands-on, total practicals along with the theory. So that will help you to make to get you really confident. Now again, towards the end of the course, there will be a live capstone project, uh, uh, and there will be regular assignments and assessments after the end of each week. So after the end of each week, there will be assignments and assessments to grade you, basically that how you are doing. And if you are lagging behind, I'll personally talk to you and help you out. Now again, I have collected lot of interview questions from my students who have attended interviews in last 1 year, and I have created an interview series out of it. So complete interview series which contains a lot of questions in the past will really help you or increase your chances to crack the interviews. And I will also help you with proper resume preparation and on how to apply for companies. Even you will get a lot of support from my side because a lot of HRs and recruiters are in touch with me who constantly ask for new and new candidates. So this is how I have designed this course wholeheartedly with the intention that if someone do this course as per my wish or as per my guidance, they will be in a position to crack top companies multiple offers, right? So I hope you have liked this session. And again, let me just talk about the curriculum at a very high level. Let me just talk about the curriculum. So you can see this is the curriculum. First week will be this, basically on HDFS architecture and all Linux commands, HDFS commands. Second week will be distributed processing with MathReduce. Third week will be Scoop. Fourth week Hive. Fifth week will be Hive Advanced, and even Yarn is there. Sixth week will be your NoSQL, including HBase and Cassandra. Also the Hadoop integrations. Seventh week will be functional programming using Scala in a lot of depth, right? Eighth week will be Spark core in depth. Ninth week will be data frame, dataset, and Spark SQL, which is increasingly important these days. Very, very important, right? 10th week will be Spark advanced concepts with optimization techniques. 11th week will be Kafka for streaming, and even the scheduling part, Uzi and Airflow. 12th week will be big data on AWS Cloud. All these things will be covered in a lot of depth. This is again a very important module. 13th week will be total interview series and resume preparation. 14th and 15th week is totally allocated for a project and also the final assessment. Having said that, assessments will be continuous also after the end of each week, and you should get at least 70% throughout to get the certificate from me. And if you do not get 70% throughout, then you won't get any support from me for the placements also, because from my side I want to refer only candidates who have done well in my course. And if you go through the videos well, if you spend 10 to 12 hours per week, then definitely you will easily get more than 70% throughout this curriculum. So I hope you have liked my session, and you can see this is a 5-star Google rated course throughout. Still, this is the actual still from one of my classroom session, right? Just in case you are wondering what image is this, right? And these are the key highlights of the course again. So I will just end the recording, and I hope you enjoyed the session. Thanks a lot.